I'm not so sure about the signs. So, are you a victim of education system who finds it difficult to assign signs in Doppler's effect? Then worry not, here's a solution. Okay, in this video we'll be discussing an amazing approach by which you'll be able to logically deduce these signs without remembering any cases or without remembering any tables. Okay, just like that. So let's get into it. So before diving straight into the sign debate, let's briefly discuss what Doppler's effect is. Okay, so like I've written over here, whenever there is relative motion between the source and the observer, now the term that is important over here is relative motion. Okay, for Doppler's effect to be seen, to be experienced, you need something known as relative motion. Okay, there should be relative motion between the source and the observer. Suppose you have the source and the observer sitting in a moving train. Will there be Doppler's effect? No, because if you see relative to each other, although the train is moving, relative to each other they are not moving. Okay, they are sitting in a moving train. Relative to each other they are not moving, right? So Doppler's effect will not be experienced in that case. Okay, so for Doppler's effect you require relative motion between the source and the observer. Okay, now what is the source and what is this observer? Let me just briefly tell you about that. So source is somebody who produces the waves. Okay, and in our discussion today we are discussing about Doppler's effect in sound, right? So source is somebody who just produces the sound waves. Okay, just produces the sound, and observer is somebody who observes it, who receives it, who hears it. Okay, so source is somebody who produces the sound, observer is one who receives it. Okay, so whenever there is, let's come to the definition. So whenever there is relative motion between the source and the observer, what happens? Okay, the frequency which is received by your observer, okay, now associated to waves you have frequency, right? Certain frequency, maybe 100 hertz, 200 hertz, whatever hertz. Okay, so yeah, the frequency that will be received by the observer, the one who is hearing it, will be different from the frequency which is actually emitted by your source. Okay, isn't that amazing? Suppose you have a source. Okay, you have source and observer, they have some kind of relative motion between them. Source is emitting a frequency of 100 hertz. Okay, so there is relative motion between the two, right? So the frequency of the wave as heard by the observer will not be 100 hertz. It can be something bigger or it can be something smaller. Okay, that depends on the type of relative motion they are having between each other. Okay, we'll come to that. But anyways, the frequency which is heard by the receiver, the observer, will not be same as that emitted by the source. Okay, it will not be same as 100 hertz. Okay, so it will be something bigger or something smaller. Okay, and this is nothing but Doppler's effect. Now it is a very common phenomena. You might have experienced it, witnessed it in your lifetime too, standing by the roadside when a car blowing horn just passed you. Okay, that time it is Doppler's effect. When the car is approaching you, you'll hear a different frequency, and when the car is departing from you, moving away from you, you'll hear a different frequency. Okay, so those are two different frequencies, and that's due to relative motion or due to Doppler's effect. Okay, that's Doppler's effect happening over there. So it's a common phenomena, you all have experienced it. Okay, so now this is the formula to find the apparent frequency. So as I said, the observer is hearing a different frequency, right? And this is the formula to find it. This is the different frequency. Okay, so this is the formula to find the different frequency that the observer is hearing. Okay, and it's known as apparent frequency, scientific term. Okay, so this different frequency which the observer is hearing, it's the apparent frequency, right? It's not the original one, it's the apparent. It just appears to the observer, right? So it's the apparent frequency. And now I have left this blank spaces because I'm Taylor Swift. No, because it depends on the sign, right? So we'll come to the sign debate just in a while. Okay, So we are supposed to decide the signs over here. It can be plus minus or plus minus over here. Okay, so we'll decide the signs based on the cases. Okay, but you don't have to remember the cases. I'll give you the approach. Okay, we'll come to that. So v is the velocity of your wave over here. Okay, this v stands for velocity of wave. Just remember the syntax. Okay, v in the numerator, v in the denominator. It stands for velocity of the waves, velocity of the sound waves. Okay, maybe 330, 340, whatever is given in the question. Okay, VO is the velocity of the observer, the speed of the observer with which it is moving. VS is the velocity of the source. Okay, and finally we have F, which is the original frequency, the frequency that was produced by the source. Okay, so this is the original frequency. Now we won't go into the derivation of this formula because it is something that can be looked up in the book, right? So I'll leave it on you. We won't go into the derivation of this. Okay, we are just here to solve the sign debate, right? So let's move into the sign debate. Yeah, all I want to say is the observer, the velocities of the observer and the source should be in the same line. Okay, but for distances very far, it can be approximated, right? If you are standing over here and the source is very far, okay, and the velocities are along different lines, then also you can hold the same formula holds over there. Okay, so let's not worry about that. We'll come to that when we discuss about the numericals. Let's move to the sign debate now. Okay, so let's discuss the amazing approach that we were supposed to. So here we have 4 different cases, okay, as you can see, and we have written the formula syntax, the general formula syntax that we discussed in the previous chapter. Okay, so now we are supposed to assign the signs over here. Okay, now again I will say that you don't have to remember the formula by the case. Okay, you don't have to remember it this way, that this formula for this case, this formula for this case. No, you don't have to do that. We are just going to deduce the formula. We are going to derive the formula every time logically. Okay, and that doesn't take a lot of time. Okay, and remembering takes a lot of energy. Okay, so don't remember the formula. We are going to logically think it out. Okay, so in order to do that, you are supposed to remember these 2 things. Okay, I'll also tell you how it works, why the y aspect behind it, but yeah, for now just remember it. Okay, so when it's towards, okay, whenever it's towards, it means it's increasing frequency. Now what did I just say? I want to say that whenever observer moves towards the source or source moves towards the observer, it is trying to increase the apparent frequency. I'll repeat that. Whenever observer is moving towards source or source is moving towards observer, it's trying to increase apparent frequency. And the other part, you can write it's away, means decreasing the apparent frequency. Again the same thing, whenever your observer is moving away from the source, it is trying to decrease the apparent frequency, and whenever your source is trying to move away from your observer, it is trying to decrease the apparent frequency. Okay, so these 2 things you are supposed to remember. I'll also tell you the y aspect, but it is not that important, but just for your understanding. Okay, I'll tell you that later. So let's assign the signs. Okay, let's try assigning the signs by using this logic. Okay, so just remember this thing, just note it down somewhere, or you can remember it now. Okay, you can just go through it once. Okay, so towards, source moving towards or observer moving towards source, it will increase the apparent frequency. If source is moving away from the observer or observer is moving away from the source, it will decrease the apparent frequency. Okay, so let's come to case 1. You can see that source, okay, let's see it from the observer perspective first. So observer is moving towards source, right? Observer is moving towards source. So towards means it's trying to increase the apparent frequency, right? So it is trying to increase this apparent frequency. You can see that the velocity of the observer is in the numerator. So in order to increase the apparent frequency, just add a plus sign. Okay, so if you have like a fraction and you want to increase its value, right, what do? one, increase the numerator, or two, decrease the denominator, right? So that is the logic we are using. Okay, so we have our observer over here, it is moving towards the source. So we can see that towards means it will increase the apparent frequency. So it is trying to increase f dash. And how will it do so? Because observer velocity is in the numerator, we'll just add it, right? So v plus vo, we are increasing the numerator so that f dash increases, right? We want f dash to increase because it's towards. Okay, you can trace it back. Okay, now if you see in the same case, the source is also moving towards observer. Okay, let's watch it from the source perspective now. Okay, so the source is also moving towards the observer. Okay, so towards means it wants to increase the apparent frequency. Okay, so it wants to increase the f dash, okay, the apparent frequency, but it is in the denominator. So how do you increase the fraction? Increase the numerator or decrease the denominator, right? So you want to increase the value since it's moving towards your observer. You want to increase the value of f dash, but the velocity of the source is in the denominator, so minus. Okay, so v minus vs, you decrease the denominator and that will increase the value of f dash, right? So it's logical. I know it's hard to digest. Let's come to case 2. Okay, case 3 you'll do it by yourself, I bet you. Okay, so let's come to case 2. Okay, so let's do it again. So in this case you can see that observer is moving away, right? Source is over here, observer is moving away from the source. Okay, so away means it is trying to decrease the frequency. Decrease the frequency. Okay, it's trying to decrease the frequency, it's in the numerator. So in order to decrease this f dash, you decrease the numerator. Okay, because how do you decrease a fraction? You either decrease the numerator or increase the denominator, right? So here you want to decrease, right? It's moving away, so you do v minus vo. Okay, so that will decrease the numerator and in turn that will decrease your f dash. Okay, let's see it from the source perspective. Okay, what is source doing? Source is moving towards the observer. You can see that observer is running away, but source is chasing it, right? Source is running towards the observer, right? So source is trying to increase the frequency. So how will source increase the frequency? In order to increase the frequency, the same case, right? Increase the frequency, you have to decrease the denominator. Okay, so in order to increase this apparent frequency, you decrease this denominator and that will increase f dash, right? So that's the idea behind it. Okay, so let's try it again over here. If you want to try it, you can pause it and discover the joy of doing it yourself. Okay, so okay, let's try it. Okay, so in third case, you can see that source is moving away and observer is chasing it. Just opposite to this case. Here the observer is chasing it. So observer is moving towards the source, right? Observer is moving towards the source. So it is trying to increase the frequency, right? It's trying to increase the apparent frequency. So here we'll increase the numerator, right? Observer velocity, v plus vo, right? Increase the numerator, increase the apparent frequency. It's moving towards, right? And source, if you see, it's moving away. It's moving away. Okay, so it's moving away. It's trying to decrease the apparent frequency, right? Source is trying to decrease the apparent frequency. So how can you decrease this? In order to decrease this, since source is in the denominator, you have to put a plus sign. Why now? Because suppose you have a fraction, you want to decrease it by manipulating the denominator. What will you do? If you want to decrease it, you will increase the denominator, right? You will divide it by more. So if you divide it by more, automatically it will decrease, right? So v plus vs, because it's you want to decrease it, right? Source is moving away, you want to decrease f dash, so you increase the denominator. So it's logical interpretations. Okay, so you'll be able to do it when we come to problems, right? Even you can try it over here. Okay, now you should be able to do this. Okay, you can pause it, pause the video over here, try it. Okay, so let's come to this case. So in this case, you can see that source is moving away from the observer and the observer is also moving away from the source. Okay, they are parting away from each other. Okay, So source is moving away. So okay, let's see it from the observer perspective first. So observer is moving away, which means it wants to decrease the frequency. So decrease the frequency, so just put a minus sign, right? V minus VU. So that will decrease the numerator, sorry, and that will decrease the frequency, right? You decrease the numerator, that decreases the apparent frequency, okay? Now, what is the source trying to do? So the source is also running away from your observer, right? So it is also trying to decrease the frequency. So how will you decrease this? The source is in the denominator. So you'll add this V plus Vs. V plus Vs, something big in the denominator makes the fraction smaller, right? So V plus Vs. Okay, since it's moving away, it's V plus Vs. A big number in the denominator will decrease this. Okay, so you just have to think it logically. I know it might not be that you might not be that satisfied by this approach, but you are going to do problems with me, and then you'll feel that this approach is something very, very good, okay, because it includes logical interpretations than just by hearting things, right? So a little bit of maths in the way, but yeah, it's very nice, right? You get a scope of thinking, and that's very nice indeed. Okay, I'll explain you how this works, okay, in the next chapter, like why does the y aspect behind it, okay, why when the source moves towards the observer the frequency increase, and why vice versa, okay. So let's move to the next chapter, okay, or else you, if you don't want to learn the y aspect, you can directly skip to the next chapter, which is based on numericals, okay. There will do numericals based on this idea, based on Doppler's effect, okay. So if you want to understand why this, then follow me up in the next chapter, okay, or else skip. So let's understand the y aspect behind this, okay. So let's take the first case wherein the observer is moving towards the source, okay. So in that case we know that it's moving towards, so the frequency, the apparent frequency should increase. Let's discuss why. Suppose we have a source over here, okay, which is producing frequency of suppose say 100 hertz, and we have an observer over here who is just standing over there, okay. So since there is no relative motion, in that case there will be the frequency heard by the receiver, the observer will be same 100 hertz, right? Now the observer decides to run towards the source, okay. Suppose it's a nice song, it's his favorite song, so he runs towards the source, okay. So in that case you can easily see that the number of waves, you can feel it, the number of waves hitting him in that case will be more than the number of waves hitting him in the stationary condition, right? Now he is running towards the source, so the number of waves hitting him in that interval of time will be more, right? The number of waves hitting him will be more frequent, okay. The waves hitting him will be more frequent, and which basically means that the frequency according to him will be more than 100 hertz, okay. The apparent frequency will increase, right, when he is running towards the source. I hope that you are able to understand it, feel it, okay. So we discussed about observer moving towards the source, and let's similarly discuss when the observer is running away from the source. Now when the observer is running away from the source, you can again go by the same lines. Suppose we have a source over here producing constant sound waves, and I'm the observer running in this direction. I'm running away from the source. You can easily see that the number of waves reaching me now have to travel a longer distance, right? And that will take time, right? So number of waves reaching me becomes less frequent, right? So that means the frequency should decrease. I should hear a frequency which is less than the original one, right? The waves are reaching me less frequently. They have to travel a longer distance, right? So when I'm running away, when the observer is moving away from the source, the frequency becomes less, okay. The apparent frequency as heard by him will become less, okay. Now let's discuss it in the source perspective. Now this is a bit tricky, but yeah, so let's focus over here, okay. So when the source is moving towards the observer, Okay, now of course the number of waves produced by the source will not change. So what is changing? Let's see that. So a source is moving. Okay, source is moving towards the observer. Okay, so you can see that suppose hi and hello are two different waves. They are consecutive waves. Okay, suppose. Okay, so which are emitted by the source. Okay, so the source first says hi, then moves some distance and then says hello. Okay, so hi and hello. Okay, so you can see that when the source is moving, the distance between these two waves is squeezed, right? Suppose the source was stationary, it says hi and then says hello. Okay, so this is the distance between the two waves. Okay, now the source is moving and it is saying hi and hello. Okay, now distance has decreased, right? The distance, since the source is moving towards the observer, the distance between the two waves has decreased, or the wavelength has decreased, or the frequency has increased. Okay, so yeah, the source moving towards the observer squeezes the two waves, and that's why the wavelength decreases, and that's why the frequency increases. Isn't that amazing? Okay, let's discuss about the away case as well. Okay, source moving away from the observer. Now it will just stretch the two waves, right? So it's very obvious. Okay, so suppose we have our observer over there and source is moving away from the observer. Okay, and it says hi hello, right? Now waves are in all direction, right? It's also going in the backward direction. It's three-dimensional. Okay, so the wave says hi and it moves a distance forward, and then okay, I'll start from here. It says hi, so it goes this way, hi. Okay, there we have our observer, so hi and hello. Okay, so when I move forward, I increase the distance between the two waves, right? So you can see that there is stretching out of distance between the two waves, or the wavelength increases, or the frequency decreases. Okay, so in the case when the source is moving away from the observer, there is stretching of wavelength, or basically the frequency decreases in that case. Okay, so that's why the frequency that is heard by the observer is less. Okay, away case. Okay, so that was the whole understanding behind applying this logic over here. Okay, so towards increases and away decreases holds. Okay, we have understood it very well now. Okay, so let's go to the numericals now. Even if you didn't understand this understanding thing, okay, so it's really not that important. Okay, but although it's worth learning. Okay, I tried my best to explain, but anyways, even if you didn't, you'll be able to do the numericals. That's all what I want to say. Let's move to the numericals. So question 1 over here, in this question you are over here and there is a siren which is moving away from you. Okay, so this is the source and the frequency of this sound waves is given as 1000 hertz. Okay, the velocity of your source is given as 10 meters per second. You are stationary. Okay, so there is relative motion between you two. You are stationary but the siren is moving. Okay, so yeah. So the velocity of the source, the siren, is given as 10 meters per second in the direction shown. The velocity of the sound wave is given as 330 meters per second. Okay, you are supposed to find the apparent frequency. Okay, we know the syntax. Let's do it. F dash is given as V VO divided by V Vs into F, right? The original frequency. Okay, now time to substitute the signs. You can see that you are at rest, the observer you are at rest. So basically the sign does not matter, it's just plus or minus. Okay, whatever you do, it's plus or minus 0, right? So yeah, that does not matter. This VO is 0. Okay, now Vs, if you see, the siren is moving away, right? Away means it is trying to decrease the frequency. Away means it's trying to decrease the frequency. So in order to decrease this F dash, it's in the denominator. So now what will you do? You will increase the denominator. If you increase the denominator, it will directly decrease F dash, right? So this is the formula that we are supposed to use. So just substitute the values now. So 330 plus minus 0. Okay, so that will be 330 divided by 330 plus Vs. 330 plus 10, that will be 340, and into the original frequency, which is 1000. Okay, So this and this will get cancelled, and after solving this, okay, I leave that on you. You will get it as 970.6 hertz, I guess. Let me just verify that. Yeah, this is the answer that you will get after calculation. I know it is a bit of calculation over there, yeah, but the answer that you'll get is 970.6, and you can clearly see that this is less than 1000, and which is justified by the fact that siren is moving away, right? It's moving away, so the apparent frequency should decrease. Let's move to the next question now. So question 2 over here, again you can see the observer is at rest, source is moving with a velocity of 30 meters per second towards the observer this time. Okay, the frequency of the sound waves emitted over here is 540 hertz, speed of sound in air 330 meters per second. Okay, again find the apparent frequency. So let's do it. So f dash will be given as VO divided by VS into f, right? Now observer at rest, so you can use plus and minus, okay, plus or minus, because it's 0, right? So plus or minus 0. And source, if you see, it is moving towards the observer, okay? So towards means it is trying to increase the apparent frequency, right? Now it is in the denominator, so you have to subtract, right? V minus Vs, so you subtract it in the denominator, which means you decrease the denominator in order to increase this f dash towards. Okay, let's do it again. Since the source is moving towards the observer, it is trying to increase the frequency f dash, right? So it will do it so by decreasing the denominator. So V minus Vs, you decrease the denominator, the fraction increases, right? F dash will automatically increase, okay? So that's why a minus sign over here. Okay, so let's solve it. So V plus or minus 0, V is 330, observer is at rest, so plus or minus 0. B 330 minus the velocity of the source, which is 30, so it will be 300 this time, and into we have 540, right? I think this is, yeah, this will cancel, this and this can get cancelled. 3 11s are 33, and 54 into 11, that will be 594, 549, yeah, a little bit of math over there, and this is your answer, okay? So 594 hertz, okay, which is of course bigger than 540 hertz, and which is understandable because the source is trying to increase the apparent frequency, right? So yeah, that's our answer. Let's move to the next one. So question 3 over here, in this question you have two trains which are moving towards each other with a speed of 90 kilometers per hour, okay? So train A is acting as the source, it's blowing its horn, and train B, in train B you have a observer, okay? So who is moving with the train, of course, he is in the train, okay? So the frequency of the sound waves emitted over here is 500 hertz. The velocity of the sound in air is given as 335 meters per second. Again, the question is the same. You are supposed to find the apparent frequency. Okay, you can pause the video here, give this question a humble try. Okay, so let's do it. So f dash will be given as VO divided by VS into f. Okay, so now let's think about the signs. You can see that the observer in this train is moving towards the source, right? In fact, both of them are moving towards each other. So it's the first case, plus and minus. Okay, I remember it, okay? But anyways, let's think it, okay? So the observer is moving towards the source, right? So it is trying to increase the frequency, right? Increase the frequency. So how will you do it? By increasing the numerator, right? So plus sign, okay? So you increase the numerator and that will increase the apparent frequency. Here you can see that. Now let's think about the source. Okay, so source is also moving towards the observer, right? Observer is over here. It's moving towards the observer, right? So it is trying to increase the frequency. And how will it do so? By decreasing the denominator. V minus Vs. You decrease the denominator and that will increase the frequency. Excuse me. Okay, so let's solve it. So V is 335 And now substitute everything in meters per second over here. Just excuse me for a second. Okay, so you have to substitute everything over here in meters per second. Okay, you can see that this is in kilometers per hour. So you just simply have to convert it. And how do you do that? You have to multiply it by 5 by 18, right? So this is the conversion factor over here. So in order to convert kilometers per hour to meters per second, you have to multiply 5 by 18. Okay, so 18, 5s are 90. Yes, and 5 5s are 25. So this is nothing but 25 meters per second. Okay, so both of these trains are moving towards each other with a speed of 25 meters per second. Okay, so VO, velocity of the observer who is in train B, it will be 25 meters per second, right? He's moving with the train. V minus Vs, V minus Vs, which is 25 again, and the original frequency 500. Okay, fine. And what will be the answer? This will be 350, I guess. 25, 360. Okay, yeah, 360 divided by, it will be 310 into 500. This and this will get cancelled, and after solving, the answer that you are supposed to get is 548.4 hertz, right? Yes. So carry out this calculation, a little bit of calculation, I know, and the answer that you'll get is 548.4 hertz, okay, which is of course bigger than this frequency because the observer is moving towards the source and also the source is moving towards the observer. So both the effects combine, okay. So yeah, the answer that you get is 548.4, bigger than 500, okay, and as verified by our understanding, right? So let's move to the next question. So question 4 over here, in this question you can see that source is moving with a velocity of 19.4 meters per second in this direction, making an angle of 60 degrees with respect to the observer line, okay. So you are supposed to find the apparent frequency given that the original frequency is 100 hertz and the velocity of the sound is 330 meters per second. Now this might seem a bit tricky. It is a bit tricky because so far we have discussed about velocities which were along the same line, right? Here if you see, the velocity is making an angle with respect to the line of the observer, okay, in line of the observer, okay. So what do you have to do? You have to resolve the velocity, okay. So break this velocity into two components. So this will be v cos theta, right? Adjacent to theta is v cos theta. So here we'll have 19.4 into cos of 60, right? So you break it this way. This will be v sin theta and this will be v cos theta, right? I hope you know to resolve. So v cos theta, so v cos of 60 degrees, right? V cos of 60 degrees, cos 60 is half, so that gives us 9.8, okay. So yeah, so the velocity in this direction is 9.8 meters per second, right? We know this. We are not concerned about velocity in this direction. You can see that it is going in this direction, right, perpendicular to this line. So it's due to this velocity there is no change in frequency, right? It's neither approaching the observer, neither departing away from it. It's maintaining a constant distance from the observer, right? It's going in this direction, right? It's not approaching, it's not moving away, this velocity component I'm saying, okay. So due to that velocity there is no Doppler's effect, right? Because there is no approaching and there is no separation between the source and the observer due to the perpendicular component. However, due to this component, you can see that source is approaching the observer in this case, right? So in that case, you can easily see that it will be there will be a Doppler's effect, right? So, and how do you write that? F dash, and how do you find the apparent frequency? It is given by this formula. F dash is V VO divided by V VS into F, right? Observer again at rest, so plus or minus 0, whatever it may be, and source is moving towards the observer. Towards means it will try to increase the frequency, right? It will try to increase this frequency by decreasing the denominator, right? So you decrease the denominator and that will increase the frequency. Okay, by the way, this is a BITSAT question. I think I found it from ACE series. Okay, so it's a BITSAT question from ACE series. Okay, so anyways, let's solve it. F dash will be given as 330 plus or minus 0 divided by 330 minus 9.8. okay, that is 9.8. Let me check it. Okay, it will be 9.7. okay, yeah, it's 9.7. yeah, so minus 9.7 into the original frequency, which is 100. okay, so you have to carry out this calculation again. I know it's a lot of calculations happening in Doppler's effect, but yeah, what can we do, right? So carry out this calculation and answer will be very close to 103 hertz. Okay, so option C, 103 hertz is the correct choice over here. Okay, it's a BITSAT question, noteworthy. And remember that you should only consider the velocities which are along the direction. Okay, both the velocities of the observer and the and your source should be along the same line. Okay, in order for this formula to hold true. Okay, so I'll give you your homework question and then we can wrap up this class. I hope you enjoyed it. So here is your homework question, question 5. So in this question, you are an observer over here. The frequency of the sound waves emitted by the source is 1000 hertz. The velocity of the source is given as 10 meters per second. Velocity of sound in air is 330 meters per second. You are supposed to tell me what will be the apparent frequency as reflected from the cliff. Okay, the source is moving towards the cliff and you are supposed to tell me what will be the frequency as reflected from the cliff. Okay, frequency heard by you as reflected from the cliff. Okay, not due to your source moving away. It's a different thing. It's a bit tricky question. So do let me know the answers in the comment section. Only do let me know whether the frequency that you hear is bigger than 1000 or less than 1000. Okay, that would do. Okay, tell me whether the frequency that you'll hear in this case will be bigger than 1000 or less than 1000. Okay, let's see who gets it correct. So that's all for today's video. I hope you enjoyed it. If you did enjoy it, smash like, and if you have doubts in some other topics, do let me know those topics in the comment section below and I will drop a video on that very soon. Okay, and yeah, that's pretty much it for today's class. Consider subscribing and keep enjoying physics.